Like I said, we're going to start right away. The session is being recorded for the benefit of those who are not here. When I look at the YouTube channel, I see that other students do access the information. So thank you for providing a forum that makes this more natural. Like I had promised earlier, I'll keep track of those who are attending, and extra credit will be awarded on the average. At least 5 points on top of your average will be awarded towards your grade. So I'm glad that you attended. Okay, so today, last time we did a lecture on hypothesis testing, which essentially was a hypothesis test for one population. So again, if you look at the website for the class, you will see that there are lectures from previous other semesters for this class. So I'm going to pull that up and just to show you. All right. Are you seeing my?
Yes.
Yes.
Okay. So you can see that there is a lecture here on the same topic. Okay, this is hypothesis testing for two populations. Okay, so that's a lecture here that you can also see from previous semesters. But again, we just accumulate this because each time there is somewhat of a difference, and future students are going to be able to see all the different takes, different presentations, and so that's also very, very useful. Okay, so I'm going to stop share this and pull up the PowerPoint for today's lecture on hypothesis testing for two populations. Okay, and again, this is going to be posted. Last time, as we said, we were looking at hypothesis testing generally, but we were testing a hypothesis for one population. What does it mean? Let's take it in a very simple way. Suppose you wanted to know, say, the average expenditure of customers that come to your restaurant. Okay, and you want to see the average expenditure for all the customers. You can look at the average expenditure for customers who eat lunch and for customers who eat dinner, and you compare the two and say to yourself, those who spend money on dinner spend more money than those who spend money on lunch. That is, now you're now looking at what you consider two populations or two samples, because lunch is different from dinner. Or you can ask yourself, what is the average expenditure of customers who come here and eat lunch? And so you look at the average expenditure for lunch, and that is one population. Now, suppose you decide to ask yourself, what is the average expenditure of males compared to females who come here for lunch? What is the average expenditure of adults compared to teenagers who come here for lunch? What is the average expenditure of Hispanics compared to African Americans who come here for lunch? Those are like, you take the same data and you break it into two and differentiate between two subpopulations. And so in statistics, in hypothesis testing and inferential statistics, we compare, we are saying that's, what do you call it? Hypothesis testing for two populations. And I see, I share some examples here. Is there a difference in the mean value of residential real estate sold by male agents compared to female agents in South Florida? That's two populations there. The gender of the real estate agents. Is there a difference in the mean number of defects produced in the morning and the night shift? Okay, and there could be theoretical reasons. Those who come in the morning, maybe they're still groggy, they're still sleepy, or those who come in the night shifts, they get sleepy and they are tired people. Maybe that could be a source of difference. Okay, maybe there's no difference because when people come at night, they have rested in the day, and so they're just as agile. Okay, or maybe the lighting in the place is a reason why people that come at night, they do not produce as well as people who come during the day or in the morning. Is there a difference in the mean number of days absent between young workers under 21 and older workers more than 60? In the fast food industry, that is two populations. And so those are examples of two population sampling. All right. And so how do you go about that? Okay. All right. So essentially, you use a statistic, the typical Z statistic that we do, but you calculate it differently. Let me see if I can present this a little bit more systematically. Okay. Before I get to that point, okay, let's see. All right. So I'm going to take this over here. All right, so that seems to be more logical. All right, so again, this is an example of two populations. And so how do you go about that? All right, how do you go about that? The first thing, I'll use an example here. Let us say we have a two population hypothesis testing houses by family size. You have lived in New York, and so you see some houses have one family and two family dwellings. And so if a house is constructed to be a one family dwelling, and other houses are constructed to be two family dwellings, is there a difference in the family size of people that live in those kinds of houses? What is the average age of two types of housing? For example, if houses are one family housing, are they older compared to houses that are two family housing? Let us think about that theoretically and ask yourself, why would somebody be testing such a hypothesis? Okay, let us say that you come to a neighborhood. Think about a neighborhood. In that neighborhood, originally, they were building one family houses. Okay. And then after many years, they begin to build two family houses. So you will find out that the average age of the one family houses will be higher than the average age of the two family houses. But there is another way where you can have a difference in the average age of the two types of housing. Okay. One could be that initially they were building more one family houses, and then they later started to build more two family houses. That could be a reason why there is a difference in the average age of two types of housing. All right. Or vice versa. Maybe initially they were building more two family houses, fewer one family houses, and then over time they begin to build more one family houses and fewer two family houses. So there could be reasons why you have differences in the average age of houses. So how do you go about setting up the hypothesis for that? Now, remember that you are comparing two population means. So the null hypothesis would be that mu1 minus mu2 is equal to 0. That is to say, if the average age of one family houses is different from the average age of two family houses, or let me step back. If the average age of one family houses is the same as the average age of two family houses, then average age one minus average age two will be 0. That is what the hypothesis will say. Okay, so you say there is no significant difference in the average age of one family houses compared to two family houses. Now, when I test you, I want you to be able to use language precisely. Okay, and it's very, very, very important. You go out there as a manager, one of the things that will help you to keep your job, excel, and indeed maybe be better than the others is your ability to present information in a way that it makes sense, in a way that is easy to understand. And so the null hypothesis will be that there's no difference, there's no significant difference in the average age of one family compared to two family houses. The alternate hypothesis is that if, say, the average age of one family houses is different from the average age of two family houses, one being, one group of houses being older than the other, then the average age of one family houses minus the average age of two family houses will not be 0. There will be a significant difference, okay? And mu1 minus mu2 could be less than 0, mu1 minus mu2 could be greater than 0, but the key point is that it is not 0. There is a significant difference in the average age of one family houses compared to two family houses. Once you set up the null hypothesis, then you select a level of significance that you would test at. Remember that. You always select a level of significance that you would test your hypothesis at. So we select 0.005. This selection is entirely up to you, okay? The selection of the level of significance is entirely up to you. It could be 0.01, it could be 0.025, okay? And once you select the level of significance, you also identify the critical z-value. I hope you remember from last time we talked about the critical z-value. And so let me see if we can still see our table. The table is not here because we used a different file. Okay. But if you look at 0.005, if you take, and I'm going to take here 0.50 minus 0.005 will give you what? 0.495. And that is where you select your z-value from. Let me see if I can find that. Okay. I'm going to continue my share. You see my screen now? Hello?
We can see your screen. The same thing, right?
The same thing, yes, the same thing. Okay. And so, how do we know that the critical z-value is 2.576? I'm going to paste. All right, see what I just pasted?
Yeah.
Okay, so now you remember we said that if you take 0.50 minus 0.005, which is your level of significance, what you get is what? 0.495. Am I correct?
Yeah.
Okay. And so we come here and we look for 0.495, and we see here 0.4948 and 0.4949, where 0.4949 is as close as 0.4951, just a little bit. And so you get 2.5. From 2.5, you go down, and 0.4949 gives you 2.57 or 2.58. Either of them will do. And so this is why the critical Z value here is 2.576, where I use the precise value because I can solve this equation mathematically myself. And so when I solve it mathematically by myself, I don't get exactly 2.57. I get 2.576, and I don't get 2.58. So those two are approximations, but when I solve the equation, the original equation mathematically by myself, I get 2.576. And you can see that is between 2.57 and 2.58. All right, but that's a whole different story. I will not ask you to solve that. This is why you have these tables that are already made. And actually, you get approximately the same result unless you are designing an aircraft for the moon, that they want to be very precise, okay? But we are not. All right, so what is the procedure now? Now, the procedure, which I'm going to insert a slide for you, okay? Procedure for testing, okay? And one then is to calculate, okay, sample mean, okay, X bar, and I'm going to insert C sample mean, calculate sample mean X bar, all right? And you calculate sample standard deviation, okay, S, just use a big S, it's not a big S, okay? And of course, then you calculate Z, okay? And Z is calculated. Let's see if that will work using, okay. You use X bar 1 minus X bar 2 divided by S1 squared over N1 plus S1 squared over N2. That is how to calculate your Z, which is the calculated Z. Now, of course, the next thing will be to compare Z, the critical Z to Z star. And you all know the procedure. Okay. Let me try to make this easier. Okay. Okay. So then the next step, like we said, so you calculate Z, and then the next step will be the decision process. Okay. Compare Z to Z star, which is compare the calculated Z, calculate Z to critical Z. All right. Then the decision rule is if Z is greater than or equal to Z star. Let's see That very strange that we can get that sign there. Good. If Z is greater than or equal to Z star, reject the null hypothesis. And the average age of houses is equal. Okay. All right. Now, if Z if Z is less than Z star, then we cannot reject the null hypothesis. Okay. And the simple thing that ordinary people say is that we accept the null hypothesis. Well, actually, statisticians are very careful. And so we simply say we cannot reject the null hypothesis, but our conclusion will usually be that the alternate hypothesis is true. Okay, that is what will be our conclusion, that the alternate hypothesis is more likely to be true. So that is the decision process, and from which we get a decision rule. And now I'm going to look at, this is an example, okay? We have two family houses. We calculated the mean for one family houses compared to two family houses. So the mean here, for example, is 4,660. The standard deviation is 1,055. There were 44 houses in the two family houses. So, okay. So we look here at average square feet of living space. We look here at average age. Okay, see there are two different averages we're looking at here. For age, the mean is 49.389, and for one family houses is 62.8, and we have two standard deviations. For the amount of living space, the mean is 4,660 compared to 4,146, and we have a standard deviation. So we're going to use those to do an example. You can see the sample, the method here. We subtract x bar 1 from x bar 2. We use the absolute values, 49.89 minus 62.8, okay? And so we take S1 squared, 29.82 squared. So we get a calculated Z of 2.29, okay? We get a calculated Z of 2.29. And so now we apply the decision rule. The decision rule, if Z, which is 2.29, is greater than or equal to Z star 2.576, we reject the null hypothesis. So my question to you right now is 2.29 greater than 2.576? I want to hear an answer.
No, it's not.
Okay, so because 2.29 is less than 2.576, which is to say that Z is less than Z star, therefore, we reject the null hypothesis that average age of houses is the same and conclude that there is no significant statistical difference between between one family and two family houses with regard to their average age. So that is essentially what we are doing. Now, what I have done in this assignment is to actually, have you calculate the averages from what do you call it, from Excel, and do it yourself. But I'm going to modify the assignment. And the way I'm going to modify the assignment is that I'm going to go and calculate the averages and install the raw calculations for you. And then what I want you to do is now to calculate your Z, to calculate your Z star, and then do your test of hypothesis yourself. Is that a deal?
Yes, Professor.
Okay. So I'm going to do the calculation, and I'll make sure I install it for you by tomorrow. Okay. If not by tomorrow, before the weekend is out, I'll give it to you. And of course, I will extend the time for the homework assignment to be submitted.
For module 5?
For module 4, actually. The module 5, we haven't even gone there yet.
So you're going to extend that too?
I will extend that. We're going to catch up. Believe you me, we'll catch up.
Okay.
All right? We will catch up somewhere. So does anybody have any other questions? Hello? You want me to go on to module 5?
Yeah,
Yeah.
can you go over
Okay.
that on the homework?
Okay. Which homework?
Well, you said we haven't got to module 5 yet, but I thought you could go over it.
Okay. Right. I'm going to go over it then. Okay. What I'm going to do is I'm going to summarize it in a synopsis. Next week, we'll talk about it some more. All right. In a sense, to, excuse me, what I'm going to do is I will go over the homework assignment for you. Okay. I will share screen so that you can see. Okay, so do you see module 5? Do you see my screen now?
Yes.
Okay, and you can see there are 2 videos, actually 3 videos on that. So you can also look at the videos, those older videos. They're on the same topic. Okay, so what is it that we are looking at in module 5? Okay, and I'm going to stop this share and pull up the other, maybe I could just, are you seeing a different screen?
No.
Yeah, I'm gonna try to pull up the right screen. Are you seeing a new screen?
It's the PowerPoint again.
Yeah, but are you seeing something different?
Yeah.
Analysis of variance.
Yes.
Okay. So now what we're going to do in module 5 is what we call analysis of variance. And for the purposes of this class, we will limit ourselves to what we call a one-way analysis of variance. There is something called two-way analysis of variance, and then there is two-way analysis of variance with interaction. Okay, analysis of variance is in fact a whole semester's course by itself. Okay, and even you know, you can specialize in it in a degree, you know, like in a master's degree or in a PhD. Okay, so it's a big, vast topic, but nevertheless, it's also a very simple concept. Okay, it's a very simple concept. Now, we began hypothesis testing by looking at one population. Am I correct? Are you with me?
Yeah.
Yes.
Okay. And then we move to the next step by comparing two populations. One family houses and two family houses. All right. We compare Hispanics to African Americans. All right. Suppose that we want to compare three or more populations. Okay. We have Hispanics, we have African Americans, we have Jewish people, and we have Asian Americans. So we now have 4 populations. Now we can have 10 populations. Okay. Now we want to compare the average. Okay. I once did a project where I compared the average family size of different ethnicities in public housing projects. Compare the average incomes of different ethnic groups, ethnicities in public housing projects. And so I looked at Asians, African Americans, Hispanics, and European Americans, so who we call white Americans, okay? And I looked at the average incomes, the average family size, or even the average length of years they have lived in public housing. Those are all, you know, different averages, but we want to compare them all together. And so what we do then in analysis of variance is we set a null hypothesis that all the averages are the same. For example, if you look at the average income of 4 or 5 different ethnicities living in public housing, you say that regardless of ethnicity, the average income of families in those public housing projects are the same. And the alternate hypothesis is that there's at least one pair of groups that are not the same. Okay, at least one pair of groups are not the same. For example, you can compare the average age of houses in Bed-Stuy to houses in Borough Park, to houses in Wicksville, to houses in East New York. You're now looking at 4 different neighborhoods, and you're comparing the average age of houses in those 4 different neighborhoods, which could actually indicate that the developments in those places were, you know, started at different times. This is one possibility. The other possibility is that more houses were built in one neighborhood, and then over time, more houses are built in another neighborhood. For example, you build 10 houses in Bed-Stuy, but only 2 houses in East New York. Then over time, you're building 10 houses in Bed-Stuy. Now you start building 10 houses in East New York. So what's going to happen is that the average age of houses will be different in those neighborhoods. Okay. Now, the difference now is that instead of using the Z statistic to do the hypothesis testing in Hanover, we use what we call the F distribution. Okay, so I want to take time and truly describe the F distribution for you. But in the F distribution, you have what you call 2 degrees of freedom, a numerator degree of freedom and a denominator degree of freedom. Okay, so we didn't talk about degrees of freedom in testing one or two population hypotheses because you were using the Z. Okay, if you were using the T statistic in those two earlier tests of hypotheses, then we'll talk about degrees of freedom. And at some point, I have to get back to that. Okay, have to get back to that. And so this is the F table and the way it's used. Okay, so I'm going to stop it here because this is a complex thing. But I'm not going to take you through how to do the problem from scratch. Okay, I'm not going to take you through that. All right. I'm going to when we get here, I'm going to calculate the means and ask you to just go through the hypothesis testing in a sense. I want you to go through the process of setting up the hypothesis and then reading of the statistic and reaching a conclusion. I want you to be able to say, I reject the null hypothesis or I do not reject the null hypothesis, and also to interpret the kinds of statistics that you obtain here. Okay, this is not all of it. There's a whole lot to it. So this is what I want to bring up for you, because after you test the null hypothesis, then you go through a next set of tests. And I would like to go through that next set of tests. I don't know why those tables are not here, but I would like to go through a whole printout and show you how to make more exhaustive, do more exhaustive tests using in ANOVA. Okay, so I'm going to hold it here unless you have other questions to ask.
Professor.
All right. Okay. So
Professor.
yes.
For some reason, I don't know why my spreadsheets are downloading and encrypted.
Which ones?
I just opened all. I'm on Blackboard right now, and I'm still downloading stuff so that I can do some work. But they're all coming out encrypted, and I don't know why.
Okay, send me an email. I'm going to replace the spreadsheets. Sometimes when they stay there long enough, they begin to act
You
up.
have like the dollar signs and the the @ signs.
Just send me an email. Send me an email. I'll replace the spreadsheets. Tell me which ones or which module, and I'll go and replace all the spreadsheets. Okay.
Okay. Thank you, Professor.
All right. All right. So good night, everybody.
Okay, good night.
Good night.
Dr. Reed.